So welcome everybody to another MIT Innotherm, the International Colloquia on Thermal Innovations. Today's Colloquia is on getting the heat out of electronics cooling from smartphones to data centers. We have the pleasure to have Professor Ken Goodson here with us, as well as the moderator, Derije Aganafer, for this session. Just want to remind you of the future events now for this Colloquia series, that there will be bi-weekly at this time on Wednesdays from 10 a.m. to 11:30 a.m. Eastern Standard. And the next session is on battery thermal management and safety on June 17th. And the following will be July 8th for extracting water from air. So it's my pleasure to introduce Professor Derije Aganafer, who is a moderator for this session. He is a Presidential Distinguished Professor of Mechanical and Aerospace Engineering at the University of Texas at Arlington. He is a member of the U.S. National Academy of Engineering, a Fellow of the American Association for Advancement of Science, and a Life Fellow of ASME and National Academy of Inventors. His research areas are in the area of 3D packaging, data center cooling, thermoelectrics, chip scale packaging, compact modeling, computer-aided electrothermal mechanical design, air cooling and reliability. It's really a great pleasure, and please join me in welcoming Professor Aganafer.
Okay, I'm going to share my screen here. Yeah, good morning. It gives me great pleasure to introduce Professor Ken Goodson, a person I've known for many years. He's the Davis Family Provostial Professor and currently the Senior Associate Dean of the School of Engineering at Stanford University. Formerly, he was Department Chair, Mechanical Engineering Department. He has received numerous awards.
Roger, your screen's not shared yet.
Oh, I thought I shared. Sorry. Share the screen. Here it is. Is it showing now? Share screen?
Not yet, Reggie.
Now it is?
Nope.
Let me just introduce him. Let me continue to introduce him then. So he's the department chair. He was formerly the department chair of mechanical engineering. He has received numerous awards. He's a member of the U.S. National Academy of Engineering. He's a fellow of the National Academy of Inventors. He has received several ASME awards, including the Heat Transfer Memorial Awards and the Alan Krause Medal. He's received the IEEE Richard C. Chu Achievement Award, as well as the AICHE Kern Award. In addition, he's graduated many students, many PhDs who are doing fantastic things at several universities, such as Professor Evelyn Wang here at MIT. His research areas include nanoscale heat transfer and electronic thermal management. So I want to quickly say about the agenda. Professor Goodson would give a 45-minute presentation, and then we're going to follow this with a 30-minute discussion and wrap up. If you have any questions, please use the Q&A button in Zoom and submit your questions. The chat feature will not be available, so all your questions, you can submit your questions at any time during his seminar to Q&A. And I want to remind everyone that this colloquium is being recorded and will be posted on YouTube, as has several past Colloquium. So without further ado, please join me in welcoming Professor Ken Goodson.
Hi, everybody. Thanks for attending. Hope everyone's doing okay. It's a pleasure to talk to you today, and I feel like I'm among friends. Dereje's been a friend and mentor for many years, and Evelyn and Gong, we work in very similar areas, and I'm sure many of the community as well. So it's fun to work on problems that people are familiar with. I mean, we have smartphones and they get hot and we think about them, and we all benefit from data centers indirectly, and it's part of the news. And so the heat management in these important structures and systems is a critical part of engineering practice right now, and it's been great to work in this area. And I had the pleasure of being at Stanford and Silicon Valley and get to benefit from interactions with lots of great companies. So the great bulk of what's gone well in my research group is owed to the wonderful engineers at the companies and tremendous students over the years that have participated. So I would like to step back and look at 80s tech. So I have daughters who are 12 and 14, and I was thinking just the other day about what I was doing with the computers and what was going on when I was their age. And my family had just purchased the IBM personal computer, which was one of the most important days in my life at that point, because I did all sorts of stuff with the computer. That thing made a ton of noise, though. There was a fan that sat inside the power supply that would blow and bring air out of that vent. But that was electronics cooling, and it was an achievement to get that personal computer out at the time. And so that's air cooling. At the same time, roughly, Cray, the Cray 2, was immersing their chips in Fluorinert and circulating the liquid and cooling it externally, and that was the supercomputer of the day, and that was super high tech. In fact, this got such a great became a reputation. It was used in a movie set for certain 80s movies that had war and various things. So that was 80s tech, and boy, things have changed tremendously. So this is an overview of the companies that we collaborate with and some of the topical areas. So there's, of course, data centers where all of the great thinking that we work on in social media and computation, a lot of it occurs in these structures. And of course, everyone has portables now, their iPhones and their devices and their Androids, and that's ubiquitous. But probably less well known is about transportation. So vehicles now have dozens and dozens of electrical devices and circuits that manage and control the modern vehicle is now really, in some ways, a very sophisticated computational device. And then there are many defense and aerospace related structures that have electronics. And I just like to drive home that electronics is pervasive, in all parts of our lives now. It's ubiquitous. And there's extreme environmental impact. I'll say a bit more about that. And that thermal management plays a role. And then there are extreme dimensions and disruptive physics. So let me say a bit more about the environmental impact. So if you look at data centers, and if you look at the bottom left, that's actually the fluid routing in a modern Google data center. So data centers are consuming a rapidly growing share of the information technology power demand. And that's not surprising. We're all using them more and more for the things we do online. And thermal management is a key part of their efficiency. So thermal management enables higher performance and reduced junction temperatures, and that reduces leakage power and total power consumption, and so can improve the efficiency of the plant. You can also design, if you reduce junction temperature or reduce thermal resistance, you're doing it actually at the transistor level possibly, or on the chip, and that provides opportunity to substantially increase the output of the data center, or to substantially scale back all this infrastructure that you see here if you want to operate at the same temperature, but you're able to do it with a more efficient cooling. And so this has actually great impact for CO2 emissions. It has impact for other types of power consumption concerns. extreme dimensions of the hallmark of electronics. This is actually, it looks actually like a dental X-ray, but it's Intel's tri-gate transistor. So we're just talking about dozens of atoms across a 14 nanometer transistor. They're so small, and this is where the heat is generated as the electrons traverse. And if you look over here at the right, you see actually the interconnects. So there's metal, and there's silicon, and then there's heat generated, and the heat has to conduct through all these complex structures at extremely small dimensions. Disruptive physics, and what I'm talking about here really is that if you look at the dimensions across a tri-gate transistor, which is doing all of the thinking in our modern computational world, you have actually, just a few dozen atoms. And if you look over here, this is from a perspective that we put together, Jungwon Cho, former student. You're in a regime where the classical tools that we learn as engineers for diffusion of heat fail, and you have to think about the ballistic transport of the vibrational waves inside the medium. Actually, Gong Chen has done a lot of great work on this area in the earlier part of his career, and he and I and a number of other people really thought hard about these problems, and many do now. But these new physics are really, really challenging and make it hard to simulate what's going on. So there's pervasiveness and ubiquity, and so the smartphone is in everyone's pocket today. And I actually think that modern portables pose some of the most challenging thermal management problems of our day. This shows actually a computed temperature distribution on the surface, the back surface of a phone. And it's excerpted from a paper that we wrote a few years ago. But one of the challenges is that they experience transient variations in external cooling conditions and some crazy packaging like this leather case, which makes it essentially impossible to cool the device. I mean, it looks neat and it's fun to have. I actually have one like this. But it makes it very difficult to manage the heat and throttle the power generation. And furthermore, there are multiple varying peak temperature restrictions, whether you're talking about the memory or the devices and the computational structures, and the geometry evolves. And there's incredibly complex and interface dense packaging. So this is one of the big challenges. And I wanted to take a moment to highlight, this is some work I did as a consultant with the Qualcomm and some collaborators there. This came out in electronics cooling a few years ago. With a data center, you pump the fluid in and you pump it out, and there's cooling, and then there's cooling towers, and it's a very integrated infrastructure. But with the smartphone, all you can really do is get the heat to the surface, and then it has to be removed by natural convection and radiation. And so a really strong measure of how well you're cooling a smartphone is how uniform the external temperature is and how well spread it is. And so we actually defined a coefficient of thermal spreading as a figure of merit to quantify the ability and the quality of the cooling of a smartphone. And it basically takes the average temperature and divides it by the max temperature. And so the bigger the max temperature gets at any given point, the lower the CTS. And so if you have a phone that's badly cooled, it has a lower CTS in this case, and it's being measured here using infrared imaging on the front side and the back and so forth. And the CTS of 0.5 has a hot spot here, whereas a CTS of 0.6, you can see it's better spread out. Now, if you were able to get uniform cooling, then you could run at an even higher power and play Crazy Birds or whatever game you wanted, or interface by Wi-Fi all day long. So this is the spreading is the key part of what goes on in smartphones. So here's a map of the power fluxes that we deal with in electronics thermal management. Now, one of the things we think about is, at the package level, we're pulling out maybe 100 watts per centimeter squared, whereas at the transistor level, we're in the megawatts per centimeter squared or even higher. And so at this level, you're dealing with lots of different power densities. And I would like to think about the packaging a little bit, and what's going on in the packaging area is pretty exciting right now of modern circuits. So the traditional package is memory and there's basically various devices that come together, and you have actually a packaged substrate, printed circuit board, and you have ball grid array, and the discrete components are interacting electrically through the package. And what's going on now is integrated to stacked dies. So you have silicon that's stacked, and through silicon vias. So actually the electrical signals are going through the signal, and this provides greater intimacy of electrical contact. Provides some thermal management challenges though, because it's all coming down through this one direction, and there's less surface area. But the future is very much fully monolithic integration, where you basically build one block of silicon with other materials that are attached, they're bonded, and you have incredibly high interconnect speeds and interactions, but it's very challenging to get the heat out of a structure like this because there's very little surface area associated with a given watt of generation. So the Semiconductor Research Corporation, which has funded my work for 25 years, and my students, funds also a new center, a relatively new center called Ascent, which is focused specifically on moving the ball forward. And the types of structures that are being investigated towards monolithic 3D circuits that involve cooling include computational elements, ultra-dense connectivity, DRAM, and then, of course, we're working on the thermal management, and so there's nanoscale convective structures and conduction solutions, actually more microscale, and there's also thermal storage structures, and then very advanced convection in these types of stacked structures. And I want to acknowledge Suman Datta, who directs the Ascent Center, and the various themes: vertical CMOS, beyond CMOS, so advanced devices that include MRAM and other types of storage and junctions. And then heterogeneous integration is a big challenge, where you bring together different types of devices. And then finally, merged logic and memory. And we're involved in multiple themes in the heat removal. So if you look, power density goes up with this type of integration. But I'd like to bring your attention to a whole different plane of power demand that's associated with power electronics. And this is, so if you think about servers, et cetera, their whole purpose is to deliver and manage and digest information. But there's a whole class of electronics called power electronics, whose purpose is to think but also deliver power. And they deliver power in a washing machine, they deliver power in a semiconductor laser, vehicle converters. They're very common in hybrid vehicles and play important roles. So this is a whole plane, and it's a little bit separated from what we usually think about of electronics, because these are all part of other products. And there's another center that we work with. It's called the POET Center. It's power optimization for electrothermal systems. And it's actually led by Professor Andrew Lean at the University of Illinois. And we have a number of great corporate partners. So these are companies like Ford, Rolls-Royce, Caterpillar, John Deere. They make stuff that uses power and needs that power to be actuated. And to give you an example, this is actually kind of an overview of the POET Center. It has a three-pronged approach where materials and devices, such as novel interconnects or high-temperature passives or thermal switches and rectifiers, and then components, such as electrical drive converters. We're working on cooling a converter together with some collaborators at the University of Arkansas under the center, and then ultimately systems and test beds, real vehicles or UAVs. And so this center is in its 5th year and is just being hopefully renewed. But here's a project along those lines that actually grew out of the POET Centers that we're doing together with Toyota. And it's a vertical power transistor. I've had the fun to think about vertical power transistors for many years. So most of the transistors that we've thought about are lateral transistors and that are integrated to do the thinking in microprocessors. But vertical power transistors are configured precisely in order to be able to block a high voltage and to deliver large amounts of power using the bulk of the body of a silicon substrate. The problem is they get really hot. So you can cool them using fluidics, and Toyota was interested in collaborating on investigating 3 separate designs that all are innovative. So the most breakthrough, challenging version would be to fully integrate the cooling inside the device. So actually you would have electrons flowing by fluid in channels that was actually extracting the heat. And this would be really challenging to fabricate, and you would need to think carefully about the reliability of the device. That's a longer-term goal. The additional activity that they proposed to us was to include the microchannels inside the electrode. So in a vertical transistor, there's an electrode on the bottom side, and you would actually, that would be made of metal, and you would actually build the channels in there. And finally, having a separate silicon-based cooling chip that attaches. And we looked at all these designs, did a lot of simulations, and then started doing some experiments. And to give you some background on how one can build a great heatsink, I actually wanted to mention here some trajectory of cooling on over the years. And you know, one of the great landmarks in fluidic cooling was the IBM thermal conduction module. And Dereji, this is slightly before you joined IBM, but I know that you're author on some great patents that came out shortly after you were there, that together with Dick Chu, and you worked on this very aggressive cooling structure for IBM's cooling. Maybe you can say a bit more about that in the Q&A session. And then now we have a modern server blade that has integrated liquid cooling from Google. And here you can see it's the fluidics are actually directly in contact with the chips, and you actually have the chance to then extract the heat and bring it out in fluids from a server blade, which is part of a data center. In between, this is my own story. So we started a company that actually built the cooling system for the Apple G5. The company was called Coology, and this massive device. So here are pumps, and there's if you take it back, it looks like a motorcycle radiator. The whole thing weighed about 8 pounds, and it would actually extract, close to 600 watts from 2 PowerPC chips that were running. And it actually was one of the great thermal management challenges of its day before multi-core came along and reduced the need for so much power density. And it was a great thing. It was fun. And actually a lot of the gamers who loved cooling kept these devices and applied them to other microprocessors to speed up their performance for gaming. And it was fun to read in 2012 and 2013, people seeing these systems finally break down and complain about Coology's liquid cooling system. Anyway, that was part of my journey. But a key part of that journey was some patents that we put out on the company. So it's not enough to deliver the fluid into channels. You have to think about how it's routed into and away from the channels, because that has a lot to do with the pressure drop. So it turns out that if you just bring the fluid in from the sides, you have a large pressure drop. But if you can route it vertically and bring it to the hot spots on the chip, and so here's your chip, here's your fluid manifolding, it can make a huge difference in the overall system performance. And so bringing that knowledge forward 15 years to this International Journal Heat and Mass Transfer paper, Ki-Wook Jung basically has vertically oriented fluid delivery that's bringing the fluid directly in contact with the chip with a low pressure drop, and yielding actually a more optimal pressure situation. So how do you make all that? Well, you fabricate the channels in silicon using etching, and if you're very careful, you can actually have it so that the channel friction is the largest component of the overall pressure drop. And so this is actually Ki-Wook Jung and collaborators from my group, also with Eric Dede I want to give him credit from Toyota. And here are some experimental data. As you increase the power, you actually go into two-phase flow, boiling, which is what we're targeting. And as you increase the flow rate, however, you can enter again the single-phase regime. So I wanted to step back. A friend of mine and Dereje's, Dr. Avi Bar-Cohen. Avi actually has a long history in the electronics cooling community, and he's now at Raytheon. He was a department chair in Maryland, and now he spent about 4 or 5 years as a program director at DARPA, and had this amazing idea of trying to push embedded cooling for electronics to its limits. So the idea of having this fluid in the channels, like we saw in the Toyota example, inside the device. And so he actually had a lot of horsepower, a lot of money, and great people involved. and he called out to the groups across the country. And Evelyn Wang was a professor at MIT at the time, and she got some great programs and work done here. And my group was in here as well, and a number of others. So the whole idea was to look how aggressively can we actually get the heat out of these devices. And my own group had just really a wonderful period of collaboration with a number of different companies and other academic groups. And the device that we were cooling was a gallium nitride HEMT. It's basically a power transistor that's used for radar applications, a lot in flight, aircraft, and various things. And it is one of the great power density challenges of our day, because it's delivering, millimeter wave signals, and the better you cool the device, the greater power density that you can emit. And the GaN provides great mobility and other electrical features, but the problem is that it's not a very good heat conductor. So typically it's bonded to silicon carbide, or in a very innovative approach, bonded to diamond. Diamond is the best heat conductor at room temperature, and the bonding then provides you a good heat conducting substrate below the functional gallium nitride. And so we were collaborating with Raytheon and Element 6 on characterizing. Turns out these interfaces were a big challenge. A lot of the heat would actually bottle up here and not go through the interface very effectively. And so a lot of the optimization work was on improving this interface, and we did a lot of measurements to try and make that work. In addition, we worked hard on building the heat sinks. So if you bond to silicon carbide, you can either then have silicon carbide plasma etching and build your fluidic channels in the silicon carbide, which is a great heat conductor, or you can actually then attach a copper, which is a good heat conductor as well, heat sink, and use these 3D manifolding techniques that I was talking about from my earlier work. And we did that together with Nuvatronics and Cree, and together with Debbie Sineski's group at Stanford, we worked on this. If you bond, however, to diamond, you have a marvelous opportunity to make an incredibly effective, albeit very expensive, heat sink made from diamond. So diamond, actually, you can etch the channels, and Raytheon had developed etching technology, and so we actually pumped the fluid through diamond, and to make the situation even more aggressive, we coated the diamond with microporous copper that would facilitate the phase change heat transfer. So we made prototypes and tested them in all of these paradigms with DARPA support. It was really an amazing time. And one of the justifications that DARPA had given was that all this work would lead to learnings that would spin out into consumer products. And in fact, here we are 4 years on, and all of our work that's going on in POETS and Ascent and these various things are directly made possible by the innovations that DARPA funded in that time. I want to give a credit to a lot of people. First of all, Mehdi Ashegi, he was one of my first students, and he's been a great mentor for my students over the years, particularly as I've done administrative work, and he was a really key figure here. Dave Altman at Raytheon, Debbie Sineski, professor at Stanford. James Palco ran a lot of these programs. He was a research associate, and now he's at UC Merced on the faculty. Yunjin Wan led a lot of this work, and she's now at UC Irvine. And Mena Aganafer was a real thought leader in working on surface physics, and so he led the program for a couple of years, and he also worked on some really great stuff on preparing surfaces so that we could retain liquid, and it was some really great science. So he's professor now at Washington University in St. Louis, and related to the moderator today. I'd also like to point out that Yunjin Wan and Demena have both recently won career awards from the NSF, a very prestigious achievement. So high risk and high yield, and this shows actually the most expensive heat sink that I know of. This is the high risk, high yield one. So we made diamond fins, vapor phase, attached to a gallium nitride device, and then porous copper on the diamond. And this shows the porous copper. And here's a top view image, and you can see the device. And we published it in a couple different places. So what's happening with this today? So we have a new program from ARPA-E that really is taking what we learned and applying it for data center cooling and for power electronics with environmental implications, CO2 emissions and so forth. By improving the efficiency of these cooling systems, we have a chance really to impact their overall efficiency. And I want to give credit to James Falco, who now is no longer a research associate with us, but is a collaborator and a great one. Also INREL, that's working on reliability, and Dr. Eric Dede, who I mentioned in the previous study from Toyota. And I want to give special credit to Dr. Michael Ohadi, a tremendous scholar all by himself, who's done a lot of work on heat exchangers, and Brenda Hendler. And this program launched January 1st. And if you look at the thermal resistance as a function of the chip area, what we did with DARPA was achieve a very, very low thermal resistance for a huge heat flow of 1,000 watts per centimeter squared. And what we're trying to do now is take these approaches and do it over a wide area device that would apply for a data center chip or for power electronics chip. So to increase it to 3 centimeters squared from a fractions of a centimeter squared. And so this extension is an extension of technology, not of physics. It's an extension where we have to deal with the fluid routing and the complexities of integration and thermal expansion, mismatch, and all sorts of things. And this is what we're doing with ARPA-E. In this moment, I wanted to step back and say a word more about diamond because it was part of the previous project. This is an artistic rendering of a grain boundary in diamond. And Aditya Sood, one of the great things we get to do at Stanford is mentor students from different disciplines. And so he's a material science student who got the PhD with my group. And he did a really fun measurement in 2018 where he scanned. We have a laser-based technique for extracting thermal conductivity down to, a micron or so resolution. And so he basically scanned our measurement approach across the top surface of a polycrystalline diamond film and was able to map out the variations in thermal conductivity, which are high inside a grain and get much, much smaller as you get to the boundaries of the grain, and the phonons, which capture the vibrational waves in the lattice, are scattered, and this shows the grain orientation. This really cool and interesting measurement played a role in our thinking about the grain sizes and so forth needed for the technology. And this gives me an opportunity to say a bit more about experimental methods. A number of us have worked really hard to develop the micro and nanoscale thermal measurements that are available. Gong Chen's group at MIT has done many great things over the years in this area. And students from his group and my group are pushing the boundaries as well. But our measurements at the nanoscale involve complex rigs. So this optical setup where you actually have pump probe requires a delay stage and high-speed laser, and you use the interaction of the light with the surface to understand the heat transfer at picosecond or even below. And then, or you spend a lot of time fabricating nanostructures and getting current to flow down them and studying heat flow. Aditya's measurement that came out in actually Nature Communications 2019, he actually built a time domain thermoreflectance system that went into the electrolyte of an immersed structure that would allow you to charge a molybdenum disulfide film. And he used this scanning approach to make the measurement of the diamond that I described previously. I'll say more about Aditya a little bit later. So let's step back to the smartphone. We've talked about power electronics a little bit and some data center work. So if the folks who design the packaging for smartphones have one of the biggest challenges. I mean, people will not tolerate a thick device. There's a huge premium on weight. There's a huge premium on the overall dimensions and the skinniness of the device. And so it's almost like we want some magic stuff to put in there that allows it to be, like I said earlier, ideally the whole thing would be isothermal at the surface, even though the battery is blocking a lot of the heat conduction, and you have some memory, and you have all sorts of different devices and sensors that are integrated there. So the package, you'd really love to have a tailored KXYZ, because you don't want to actually have infinite communication between some devices. And furthermore, you'd like it to have transient absorption. So you'd like to be able to, get on the web and do some intense, I don't know, social media or whatever you're doing on the phone, and do that for a while with super high power generation and have that energy be absorbed so that later on, when the phone was not being used, it could gradually be released, because the bottleneck here is the convection or radiation from the surface. So you'd like to have materials that stored energy without being heavy. It's not something that we can imagine doing easily. The spreader that you might integrate, that's shown here, would be, also to have these same features. The battery, you'd like it to do some of these things as well in the case. And compliance, everyone talks about wanting a phone that you can bend. So this compliance could be a key role. And you might also like it to have this absorption so you could actually, play games and stuff and release the heat later. So back in 2006, some colleagues had written a great paper, and I was invited to write a perspective in science. And I spent a lot of time thinking about thermal materials. And if you track the density and the thermal conductivity of most materials, they follow kind of a simple proportionality, where as things get denser, they conduct heat better. So diamond up here and copper, 1,000 watt per meter Kelvin ballpark, and then you know the aerogel, zero gel, things that were used to back in the day to protect the shuttle during re-entry because of very low thermal conductivity, are highly porous. And so things are essentially along this line. If you actually, however, try to make a super dense thermal insulator, well, that's hard. It can have a big impact. Or if you make a porous heat conductor that actually has a low density, that could be very important. And so one of the things I was thinking about is the areas of impact would be in those realms. And in fact, there's work that we're doing in my group on trying to develop a solid state thermal switch to route heat that takes advantage of low thermal conductivity at high density. And we're doing both for the Ascent and the Poets Center to make super small vapor chambers that take advantage of high conductivity in porous media. And so high conductivity in porous media, you can either use carbon nanotubes. We did some work on that in the early 2012, 13, 14. Or you can work with porous metals that are highly systematic in their structure. And that's something we've been working on more recently. So how do you make a metal nanostructure? And here we're really borrowing from the photonics community, which has made metal metamaterials, and also ceramic and other materials, metamaterials that allow you to modify the transport of photons. But there's actually an opportunity to take some of these fabrication techniques and apply them in the area of heat transfer. So traditionally, metal structures for heat pipes and other devices have been made using sintering of balls or wires or other types of structures, and they're relatively crude in their geometric precision. If you actually, however, start with a nanowire based on a polystyrene or other type of structure, or if you start with an array of beads of polystyrene, and you can get them in a close packed structure with dimensions down to 10 microns or even less, you can then electroplate around that structure and generate a highly systematic porous medium. And you can do it actually inside a channel, because you can electroplate along the walls of the channel, and through subsequent electroplating events you can change, for example, the pore size. And this shows an example. And what happens is you actually pack a fluidic channel with these polystyrene spheres, and then you electroplate from the perimeter, and then you actually are able to get this kind of coating, conformal coating around the sides. So that's a fun way to make progress in this regard. So one of the exciting things that you can do is then look at classical sintered copper, which is here, and you have basically, this is the permeability for fluid flow in classic sintered copper, and then you have thermal conductivity as a function of the permeability. And here I'm showing actually, you can actually get very high thermal conductivity using, for example, carbon nanotubes or other devices, and the permeability remains a little bit low because they're kind of densely packed. On the other hand, if you are able to do this template-centered copper, you actually have the chance to make both a high permeability and a high thermal conductivity at the same time. So it's not diamond high. Diamond is 1 or 2,000, but it's pretty high compared to a porous medium, and the fluid permeability is high as well. So why do we care about fluid permeability? Well, the answer is that you want actually to build a convective structure through which the fluid can flow, but you want the heat to be able to flow in as well and to flow effectively by means of the solid structure. And so I'm going to give some credit to a recently graduated student, Qi Cheng. So she did something pretty interesting and creative where she sintered the polystyrene spheres after they were deposited, and that caused them to change their shape, and in particular the necks where they interact with each other would grow a little bit. And then when you subsequently did electrodeposition and etching, you were able to control the necks or the connection points between the porous regions and the pores inside the metal structure. So it was a very sensitive way to control the pore size by means of the capillary, by means of the polystyrene sphere size, but she was also able to control very carefully the neck size connecting the two. And it allowed her to do some really interesting investigations of the physical limits that are associated with convective devices. Now, many of you may know, but you may not know, is pretty much every laptop and a growing fraction of portable devices have heat pipes in them. A heat pipe is essentially a long structure that has a porous medium integrated inside, and the porous medium wicks the liquid that's inside to the hot region. In the laptop's case, it would be the microprocessor, and then it evaporates, and then it recondenses in the cold portion, and that would be typically near the fan in the device and near some holes where the air is blowing out. And so these heat pipes are limited by the distance and how long you make them, and that's something called the capillary limit. If you make them too long, there's not enough pressure head generated by the capillary forces to pull the liquid through the porous medium. And then there's a boiling limit associated with the physics of boiling that happen actually at the hot spot. And so as you make the wick thicker and thicker, and as the copper inverse opals thicker and thicker, what happens is you increase the capillary limit. This is the total achievable heat flux. But if you actually make them actually too thick, then it becomes harder and harder for the convective boiling, or the boiling that's occurring, to make it out through this thick porous medium. And there's also relevance of the necks versus the pore size, which she investigated. There's also the wicking length and the impact on the boiling limit. And if you get actually to critical wicking length, you're basically balancing the needs for boiling physics with the capillary length of the structure. And one opportunity is that if you make these porous media, you have an opportunity to really improve the balance between capillary and boiling limits. So one other interesting aspect, and it's been kind of a major challenge and aspiration of many of us working in this area for more than a decade, is to try and develop thermal materials that can switch. And so can we make a material whose thermal conductivity can be controlled and can vary by as much as 10, 20%, or even a factor of 10, an order of magnitude? And so that brings us to a device that Tanya Liu has been working on in my group with the Poet Center support. So she's been working on a tunable passive thermal regulation device, which uses liquid vapor phase change. Now, the idea here is that you actually control the heat flux from a device as you control the non-condensing gases, and you actually have a threshold above which the device no longer is a good heat conductor. And the application of this device is, for example, in the startup phase of an engine, in a diesel engine, where you actually want it to be well insulated early in its, if on a cold day, you'd like it actually to retain heat, but once it gets to a certain level of heating and temperature, you would like to actually stop to become more effective and cool itself more effectively. And so what happens here is, as you approach the phase change temperature, you start to have much more effective heat transfer, and the insulation properties break down. And you can tune this by means of the non-condensing gases. Another thermal switch that I'd like to mention briefly is purely solid state. And this is again Aditya Sood and his work together with Eric Popp, Yi Sui, and a number of other collaborators. And the idea here is to take a layered structure, in this case molybdenum disulfide, that actually has van der Waals attachment between the monolayers. And we know that van der Waals forces are not very good at conducting heat. And in fact, some of the lowest thermal conductivities in dense materials have been reported through stacked monolayers of this type. The interesting thing that we worked on here was to view the material and the stack from the perspective of an energy storage mechanism, and have lithium ions that would intercalate and transport into the stack. And so this is actually a mechanism for energy storage that's part of the story around batteries and so forth. We were interested in the impact on heat conduction through the layers and what happens as you bring in the lithium atoms. And so what we discovered in the end is that there was a 10 times reversible, fully reversible thermal conductivity change. The challenge with this measurement, and this is really a credit to Aditya, who had done the measurements earlier on the diamond that I mentioned, he was able to actually develop an in situ measurement where you actually have the thermal conductivity measured as a function of time and also scanned over, so as a function of time as you lithiate and bring in the lithium atoms, and then as you delithiate, and then as a function of voltage, make the measurement as well as a function of time, and as you change the concentration of lithium ions, and you also change the conductance as well. And so the conductance you'll see is going up and down as you actually reduce the lithium ion fraction. There's a little bit of hysteresis that's going on here. And he actually did scanning of this in real time as the lithium ions were coming into the structure. And so he's got this video. I have no idea how well it'll play. I'll play it a couple times. So here's the lithiation process. So the lithium ions are coming in, and we see that we're migrating to a higher conductance as we go to delithiation, and it's coming back out. And so let me play it again. So this is a flake of the material that's immersed in electrolyte, and you're controlling the voltage on the flake itself as well as the biasing voltage in the electrolyte. And then you're scanning the thermal measurement across the entire flake during the measurement and imaging of the temperature of the thermal resistance profile. And so let me play it again. It starts out at high conductance, then the lithium ions come in, low conductance, and then they diffuse back out, and you're back to uniformly high conductance. And so this, in essence, was a thermal switch, which had us very excited about the potential of trying to build more practical devices. And with that, I actually will conclude my talk and acknowledge great cooperations over the years. Actually, it's been, when I first started at Stanford in 1994, it was really Intel and IBM that we were collaborating with, and it was all about workstations. And so it's been a great pleasure to expand some of the most insightful and deep thinking research we're doing today is with Google, some great partners there that have given us freedom to look at, they're thinking very carefully about the impacts of fluidic cooling on their data centers. Toyota, very creative company, great people, the research center in Ann Arbor in particular. Raytheon has been a great partner over the years in the defense space and these high power electronics. And Ford, a great collaboration now, also Bosch, and Analog Devices has been a great partner as well. So these are great companies, and we're fortunate to work with them. I also want to acknowledge we have a backbone of federal support that includes NSF, of course, through the center, among other things. ONR has been a sponsor a number of times over the years. Of course, the major program with ARPA. And of course, as I mentioned, also Domena Aganeffer, who's related to our moderator, was a great contributor in the recent time before joining the faculty. And with that, I will conclude my talk. Thank you. Thank you for attending today.
Yes, congratulations for a superb talk as well. I've listened to Professor Goodson so many times, including our campus a few years ago. So thank you. At this time, we're going to we have some questions for you from the audience. One of the questions is about microchannel cooling of power transistors. Are you stably using boiling or staying at single phase? And how about the future? This is from Shigeo Mariami.
Hi, Shigeo. So it's always a balance of risk. I mean, the two-phase flow is so exciting because you can have the lower pressure drop and you can get to the high heat transfer coefficients. As I experienced at Coology, we built and we raised money for cooling the Apple G5 around two-phase flow, and we were very excited about it. But when we ultimately got down to the 6 months before winning the engineering challenge and getting product shipped, we converted back to single-phase flow for meanings of, and the reasons were flow stability, and there are complexities in pumping a two-phase system and having it actually be stable. And so the answer is, with Toyota and the other companies right now, there is an emphasis on single-phase flow because I mean, we're in the practical phase of research, and what are the fabrication challenges to get those devices. But all of those companies, as well as the data center company Google, are pushing us to look at the two-phase flow because they see the implications for overall power consumption. So in the long term, the great groups that are working on this, and I'm thinking of the folks working at Purdue, Maryland, and Evelyn's group here at MIT, who are thinking about two-phase flow and surface modification to try and stabilize it. I think in the long term, it's going to come. It's just that for the near term, getting the power electronics companies to adopt these technologies, integrated, embedded, single phase will come first.
Thank you. Next question is from Chandar Sharma. He said, Professor Goodson, thank you for the great talk. How do you see the feasibility of implementing phase change cooling, flow boiling, evaporation, and large-scale commercial systems such as data centers?
So I actually am. I'll elaborate a little more on what I said to Shigeo. So there's, data center cooling is a art and a craft and a science all in its own. And there's a recent book out from two Google authors that you might look up on data center infrastructure, just came out last year. I spent a lot of time with that book over the last few days thinking about it. And there's so much complexity in the design of of that infrastructure. So, but if you my expertise, you get down to the chip level really. And so if you have, two phases interacting with the chip, it makes life more complicated because of the fact that you have highly variable pressure drop with the exit quality of the fluid. So basically, if you're exiting with a lot of gas phase, the pressure drop climbs pretty steeply. On the other hand, if you're exiting with just a little bit of the gas phase or in the single phase, then it can climb again as you have higher flow rates. And so you have essentially a U-shaped pressure drop challenge. And so what happens is that the system can, for a given applied pressure, you can actually have two stable operating states, one in single phase, one in two phase. And what happens is that for a given power, the system may oscillate between these two states. We saw this, and we see this in our own systems. We see it. So that's the challenge with it designing any two-phase system, is allowing it to operate stably. And then the heat transfer coefficient changes between those two states. So the big challenge that we all face in convective boiling at the system level is building a stable a device that will operate and maintain its high heat transfer coefficients and so forth, even as the system experiences changes in ambient temperature, changes in power distribution, etc. That's a system level concern. At the heat exchanger level, the phase change offers additional complexities in terms of corrosion and fouling associated with phase change that one needs. Those are manageable things that need to be handled over time. Although I would say with data centers, the idea of having these fluid routing lines and interacting with more system components does complicate the maintenance of the purity of the fluid and the fouling issues. So folks are looking at single phase because it offers relative implementation simplicity while acknowledging that phase change is the big win. The other thing I will say is that we and others, Michael Ohadi at Maryland, now at RPE, and others have shown that there's a lot to be gained in single phase through very careful design of the fluid routing. So back in the day, the exciting paper in our field, actually before I was still not even in high school, 1979, 1980, Tuckerman and Pease etched channels in silicon and pumped the fluid through. They had actually 1,000 watts per centimeter squared with a modest temperature rise. They had a huge pressure drop in those channels. So that's single phase liquid flow. We've come a long way since then in recognizing that the proper way to implement single phase flow is more like the human blood system with capillaries that are big in the arteries, and then they have these teeny capillaries that actually do the busy work of interacting with the cells. If you look at the design we're doing for Toyota single phase, or the design we're working on, some of them with RPE support and with Google, it's actually got teeny little channels that interact and do the busy work of the heat extraction that are rapidly growing in size to more arterial type structures and manifolding. And so instead of a Tuckerman and Pease type structure where the fluid is going all the way down the length of the channels and you have a large pressure drop, you just have a teeny little capillary that interacts, and then it expands out to a more larger structure. And so a lot can be done with single phase flow to make it much more sophisticated and effective than a traditional cold plate. And so there's a lot of harvesting to be done of optimization improvement for single phase flow, even as we work on the two phase structures. Perhaps that was a bit long, but I just wanted to provide some context.
Thanks for the great answer. And especially, I'm glad you mentioned about system level cooling, and especially sometimes young professors have a tendency to focus at the module level or the device level and not worry too much about how to integrate it at the system level. And eventually it fails because it doesn't get into a product. So I think it's very important to keep that in mind. So I appreciate you mentioning that. I have another question from Jorge Alvarado. And he asks, in electronic cooling applications, how close are we to the physical limits of what we can do in solids and liquids?
Wow, that's a great question. I did mention we're really after magic materials now. We want materials that have combinations of properties that nature doesn't provide us. We want a material that is a great heat conductor, but is also flexible. Well, all of the good heat conductors we know of are rigid, diamond and copper and so forth, and the flexible material polymers and so forth are lousy heat conductors. And now there are ways to push the boundaries here. So actually, one of the really Gong Chen's group has done some really great stuff, but one of the really exciting things that came from his group, it's been a while, was to show that if you aligned the molecules in certain types of polymers, you can get a pretty drastic increase in the thermal conductivity. And that was a very fundamental measurement. And so one of the things that a number of groups around the country have been trying to do is harvest that to make polymer-based packaging materials that are better conductors than the lousy conductors they are today. And actually, some of the very early work in my own group, Katsuo Kobayashi, showed that alignment of a bulk polymer film could give you an increase by a factor of 6 or 7. I think Gong Chen's group showed a much higher through actually pulling the strand between a probe and a surface. So that actually is pushing I wouldn't say they're physics limits, because the thermal conductivity along a molecular strand is a limit, I suppose. And we're trying to approach that limit through the configuration of the molecular structure in the packaging materials. So that's the package level. I would say at the device level in the silicon, there's not much we can, there was a lot of talk around, well, we should have thermoelectric cooling at the device level. And there was even, we should integrate, graphene with transistors to help with cooling. That's all exciting. Graphene is a very good heat conductor, but it's really hard to do anything at the device level that's not going to screw up the amazingly and exquisitely balanced electrical transport physics at that scale. The electrical engineers I work with and collaborate with are super good at building these devices with high mobility, low loss, low leakage, and it's very hard to go in there and adapt them thermally. I actually, some of my greatest memories are working with super bright electrical engineer. Back to my PhD thesis at MIT, I remember working through the night as we worked together with Lisa Su, who went on to lead great companies as a manager, both at IBM and AMD. Lisa and I did our thesis works together, and I remember we were making measurements on SOI devices, silicon and insulator devices, and I'm saying, well, why can't you just change this thickness? And she said, that there's just how the electrical engineers designed these so carefully that the thermal considerations of that scale are very hard to implement. And in a modern sense, these FinFET transistors are so exquisitely balanced. And we're related, you've got a couple dozen atoms across, and they're vibrating, and we talk about phonons, we're really talking about atoms that are vibrating, and it's at the limits where new physics are playing a role. So I don't know how well I answered the question, but I talked about a couple of the physical limits.
Ken, it looks like you got a lot of people excited, so we have plenty more questions for you. So one of the questions from Tejaz Hajani, and he asks, can we use nanofluids in electronic cooling? I know there's been a lot of work in that, but I don't know how much success. So can you, that's my paraphrasing, the last part.
Yeah, nanofluids are a topic that got a lot of excitement, particularly about 10 or 12 years ago. In my own group, we got some O&R funding and looked at it pretty hard. Mark Spector invested in my group, and Patricia Garagotslu, who's now a manager at Sandia National Lab, did some great work along with some other students. We made some measurements and did some modeling, and there were, gosh, dozens of groups worked on in this area. I mean, the tricky thing with the nanofluids is that the inclusion of the aggregates and the particles, it's hard to get them to actually conduct as well as a true mixture. And so the experiments we did showed that the nanofluids, when you could get them to remain in suspension, would not give you enough of a thermal conductivity augmentation to pay for the complexity they bring and the purity of the system and so forth. So there, and I'll share it. I mean, one of the challenges with the nanofluid measurements is it's very hard to do rigorous measurements because if you have a probe-based thermal conductivity measurement of fluid, the aggregation of the particles around the probe can complicate the data. And so, and in a convective structure, whether the fluids and the particles remain in suspension is very tricky. So we concluded that it'd be very, very difficult to have an impact in practical systems at the time.
Yeah, thank you. Another question, this one is from an anonymous attendee. And the individual asks, can you talk about the current status of CFD/thermal modeling for microscale electronics cooling devices? Do we still rely mostly on experimental measurements?
Another great question. And I had a whole slide on the modeling tools that we use and didn't include it for time. But, we do our simulations using Fluent and COMSOL integrated. And so I was going to make a point about the conduction first before getting to the CFD. So, there are actually at the device level, we're at a regime where, you need to account for ballistic physics and these things. From a practical point of view, the simulations that are happening of the modern devices, they use modifications to conventional bulk heat conduction physics with reduced conductivities and so forth to account for what's going on at that scale. My group did some of the Boltzmann transport simulations for electrons and phonons integrated back in the 2008-10 timeframe. That was Eric Popp, who's now at Stanford, and Sanjeev Sinha. And that was a kind of a watershed, Sanjeev's at University of Illinois, watershed simulation, in that it was the first fully coupled electron and phonon in a transistor. But here it is a decade later, and the simulations that are going on in modern devices at the companies are still continuum-based with modifications to account for the reduced conductivity in the fins. Just because the computational cost of a particle-based simulation is so incredibly difficult. Now, there are groups that do atomistic level simulations for the physics of it and for understanding, but the practical simulations that are happening at the companies are done, and are done using more bulk models, modified bulk models. I don't see that as a fundamental problem. I mean, I think that the groups that work on the atomistic modeling and so forth can inform the bulk simulation tools. So now when you step out to fluid, and you asked about CFD, there's a lot of sophistication around meshing and fluid routing and so forth for single phase. So that's moved along incredibly well, and the meshing algorithms that are available corporately. The two-phase flow is a different matter, and the structures that are being developed and the physics of the phase formation and the distribution of the phases and the transport of the vapor and so forth It's very empirical still, as you mentioned, reliance on experimental data and the models. And the boundaries are really getting pushed. I mean, you have people who are modifying surfaces. So Evelyn Wang's group has done a lot of leadership things in terms of super hydrophobic surfaces for enhanced condensation and boiling, and et cetera. And so you have the situation where there are new surface physics at play, which fundamentally change the modeling needs. And you also have new regimes of capillary forces enabled by the types of structures I was talking about. And so really there it is highly empirical, and the folks who work on the CAD have to rely on simulations. So at that level, we are very, very much working, in terms of what we're able to get in terms of data.
Great. Interestingly, we had a paper with Professor Christina Amon, you know very well, on non-uniform power silicon, and it was significantly different, our simulation based on continuum mechanics and her simulation based on MD. So we actually adapted some of her work, and it made a difference. But
I agreed. Actually, Dereje, I didn't mean to say the effect was small. I just meant to say that folks who do the atomistic stuff, like Professor Amon and Professor Chen, Gang Chen, and among others who work in this area, there are ways that you can adapt those findings into continuum models to make some progress.
Yes, hierarchical models. Yes, absolutely. Thank you. You have another question. This is from Jiajian Luo. And Jiajian says, Professor Goodson, I really like your fantastic presentation. I would like to hear your opinion about the heat transfer in 2D materials. Do you think it's a promising area in the near future? And what are the challenges that we are facing in that particular area?
Well, I mean, it captures the imagination, no question. And actually, my former student, Eric Popp, did some amazing measurements in graphene and related structures after he left my group. So the tricky thing with these materials, so we work in this monolithic 3D ascent center where we're trying to develop monolithic structures. And one of the things we talked about, also together with Eric, who's also in the center, is, can we incorporate these incredibly high, just give you, so the thermal conductivity of diamond, 2,000, or if it's isotopically enriched, 3,000 watt per meter Kelvin. Some of the early measurements that Arun Majumdar's group did and Eric and my group did on carbon nanotubes showed that it could be approaching those levels for a single nanotube. And then Eric went on to make great measurements and others on graphene, getting very high conductivities. And the problem is that the thermal conductivity is extremely high, but the cross-sectional area for conduction is so low because these are nanotubes. I mean, these are 2D materials, 1D materials. So the actual amount of heat being removed is pretty small. And so the whole idea of having a graphene layer built into a monolithic 3D circuit, actually, in terms of the amount of heat you're able to spread, it's actually not that huge. And there were some simulations that were done also for power transistors. If you were to drape graphene, et cetera, over the surface, the thermal conduction would, while the conductivity is high, the conductance is still relatively low and the impact is low. The other complicating factor, and I've gotten my fingers burned a little bit in this, my group worked for a number of years on carbon nanotube-based interface materials. So the idea there was, can we have 1D or 2D inclusions that are built into a organic matrix? And so if you have a carbon nanotube with a 3,000 watt per meter Kelvin conductivity embedded in a flexible matrix, you can have your cake and eat it too. You can have a high thermal conductivity, but you have a compliant interfacial material that can be used. And that was the dream. And we made structures that initially had very promising thermal and compliance properties. Yunjin Wan worked on that. Amy Marconnet, who's now a professor at Purdue, worked on that. And that was all great, but we discovered that these carbon nanotubes and these low-dimensional structures are very, very delicate, and they get damaged very easily. So you would make a measurement and have a great result, and then actually after some cycling of the strain, you'd actually find that the measurement, the conductivity wasn't as high. So they're very delicate materials. So integration of some of the 2D structures into practical systems is very, very tricky. So where could this have impact? I think actually, engineering true, nanoscale circuitry where the heat generating components are in fact suspended on graphene film, or in an arena where the dimensions of heat generation are comparable with the thicknesses of the molecular scale, then this becomes interesting and provocative, and it's really at molecular or nanoscale level electronics in the frontier where it could be potentially exciting, where the dimensions of the electrical devices are scaled down.
Right. I have a question for you, just a thought you might want to share with us. Like you mentioned, the thermal conduction module was introduced in the early 80s by IBM. It was indirect liquid cooling. And so liquid cooling has been around for a while, but not necessarily made that much progress. And then with data center cooling, there's, allowable zones where you can only bring the inlet temperature 18 to 27. Now you can go all the way to 45. But then as the silicon, as Intel and so on start increasing their power, I don't know, 120, 150, then you might have to go backwards. You'd be forced to either reduce, because the thermal budget is fixed, right? Reduce the inlet temperature, or start seriously looking at liquid cooling. So, and I know companies like Google are looking at, in their AI systems, looking at liquid cooling. But what do you see? Can you excite some young researchers about their work in liquid cooling so they can extrapolate, yes, there is more significant interest in that besides what we've seen in the past?
That's a great question, Reggie. And actually, I mean, the stuff going on in my own research group, and I want to credit Mehdi Ashegi for his great contributions right now. But we're actually, I keep meaning for us to get into new stuff that's energy conversion and other areas and we have had projects or nano bio and other things, but the interest from companies right now in liquid cooling, near-term single-phase, long-term two-phase, is just overwhelming. We can't satisfy all the customers who want us to work on their systems, and power electronics in particular. And so, I mean, it really is happening, I think, that it's being driven at the corporate level. The other thing I'll say is that, the history of liquid cooling has this very long dance between the incredibly clever electrical engineers and the thermal engineers. So Tuckerman and Peace came out, and then that shortly thereafter NMOS became CMOS, which doesn't consume nearly as much power because of the way the logic works. And then so suddenly the need for liquid cooling was set back a decade or so. And then we built these 3D very sophisticated structures to reduce the pressure drop on what Tuckerman and Peace did, and built the Apple G5 heatsink. And that was a power PC chip generating 1,000 watts per centimeter squared. And that thing was just incredibly difficult to cool because the dimensions were so small. And then the next year, Intel came out with multi-core, which basically has multiple versions of that core smaller that bounce around when they get too hot. And that set liquid cooling back by 4 or 5 years, or I should say set the world forward by 4 or 5 years and made it unnecessary. I mean, it's clever design, but the double E's are running out of these quick fixes, and they are approaching physical limits, even with the multi-core, et cetera. And certainly in powered electronics, you can't play a lot of these tricks. and so that's why we're seeing the situation there. And you read a book on data centers, and the optimization that's already gone on there is so extreme that anything you can do at the device level with liquid interaction and so forth is going to have a big impact. And so I think it's happening, and there's plenty of room to engineer this, not just in the academic world and going out at these companies and making it happen.
Yeah, I appreciate the fact you mentioned heterogeneous integration as the frequency for technology nodes is growing, right? It used to be 1 year, 2 year, now 4, 5, 6 years. You still got to get performance. So packaging and cooling, which is a major part of it, will play a role. So thank you for that. I want to ask Professor Wang and Professor Chen, how many more minutes should I go? Because I got, I think, some infinite more questions. So obviously, Professor Goodson, very popular. So how many more questions should I, maybe 2? Yeah, okay. I'll 2 more questions, we'll stop, right? So here's someone, Harish S. He was actually in your lab. He says, Professor Goodson, I'm a former visitor to your lab in 2011. How beneficial is it to use organic phase change materials for electronics cooling? There was PCM question earlier. But.
Yeah, I mean, it's always been a dream to have these thermal capacitors that would solve problems. I mean, I think it's most exciting in the mobile space because mobiles are so limited in their cooling to the surface. On the other hand, the big challenge with these organics and phase change is getting the heat in, and so this is an example where you need to have a matrix that can store, but also you need to have a matrix that can conduct as well. And so I think, and I in the consulting framework, I've seen some promising simulations, but I think in the end, it really comes down to the design of the system around these mobile applications.
Okay, I think I will end it with one more question. Energy, I know you do a lot of things besides cooling. So one question is for Ali Rajabapur. And the question is it possible to convert generated heat from electronic devices into electricity, like using thermoelectric devices?
Yeah, I mean, it is possible to harvest energy. The problem is that the delta T is pretty modest compared. I mean, the energy conversion that we worked on in thermoelectrics and so forth has been relatively high quality heat. It's coming out at 800 degrees and so forth that are higher, where you can benefit from a large temperature differential. The idea of harvesting just a little bit of heat from electronic device that's coming out, at 90 degrees or 80 degrees, it's very hard to get any reasonable level of efficiency that would contribute to the system. And so we've looked at it, and others have encouraged us to look at it, but it's very hard to see it in a practical framework. I do think that waste heat recovery is quite promising in higher temperature applications in manufacturing setting and combustion setting and so forth. There's real tangible benefits, but electronics is much harder to see.
Thank you. And I think at this time, let's give a virtual round of applause to Professor Ken Goodson for this outstanding presentation, because I only got 1,000 more questions. So would you like to say some final words?
Thank you, Dereji. Appreciate it.
And I'm going to pass the baton to either Professor Gang Chen or Professor Wang to say some final words.
Okay, so I'll just remind our next talk. I think Emily had to bail out. So let me just share my screen, and so our next talk will be on June 17, and this will be a very interesting panel, safety, and after so please we'll send a reminder, but 2 weeks later we have the same time and same link. And just if you have online, you can visit the past recording and at inotherm.mit.edu. Thank you, and thank you, Diraji. Thank you, Kim, for a really inspiring talk. Thank you. And we will stay, so after we end this, the website will stay open for a few minutes if you have more thoughts or question or direction to share with us. Thank you.
Thanks a lot, John.